Okay, so we will start with this new lecture today, lecture 19, in which we will talk about covalent solids, and if we are able to finish that early, we can start ionic solids, but it's unlikely. So let me just recap what we have studied so far. We looked at in the past few lectures, the structure of metals. Okay, so structure of metals typically is of three types. Most metals are FCC structured, or you can say CCP structured, cubic close packed structured, or hexagonal close packed, and BCC structured. There is only one example of simple cubic metal, which is polonium, but by and large most of the metals and alloys fall in this category. Now, so FCC based structures materials were typically things like gold, copper, etc., nickel. HCP based materials are magnesium, cadmium, etc., and then BCC based materials are, for example, titanium, tungsten, molybdenum. All of these are BCC structured materials. Now, the alloys, most metals do not exist in pure form, and we also use them in impure form for improving their properties. For example, iron is used as an alloy of iron and carbon, because carbon is intentionally put to make iron stronger. So the question arises is, where does carbon go? For example, similarly we also use brasses and bronzes, which are solid solution of tin and zinc, or zinc and so you can have brass, which is CuZn. You can have bronze, which is CuSn, and you have steel, which is iron carbon, and there are many other examples. These are three famous examples of materials that we use in regular applications. So where do these atoms go? For example, where does zinc go, where does tin go, where does carbon go? So it happens, it is determined by the size of the atom, it is determined by the size difference between the host lattice and the impurity atom, it is determined by the valence difference, the structural difference, and so on and so forth. So it turns out that carbon and iron will make an interstitial solid solution, whereas zinc and tin will make a substitutional solid solution, because the size of zinc and tin is larger than the size of interstices that occur in these solids. So carbon prefers to go to interstitial size because it's a smaller atom. So whether it's a gamma iron or alpha iron, depending upon the temperature, it goes in interstitial sites, whereas zinc and tin, below their solid solubility limit, they make a substitutional solid solution. And then we also saw some examples of compounds, which are, so you can have line compounds which have fixed composition, intermetallics. Line compounds and intermetallics can often be similar also, and then we also looked at electron compounds. So these were three compounds which form when you mix two metals with each other, and they tend to have fixed composition. And for example, electron compounds, they have fixed electron to atom ratio. Similarly, intermetallics, like Fe3C, for example, is a line compound, it has a fixed composition. You have intermetallics like Ni3Al, CuZn, and so on and so forth. Electron compounds, we looked at some CuZn type of compounds system which has specific electron to atom ratios. So these are all materials which are metallically bonded materials predominantly, although intermetallics and line compounds may have some fraction of covalent ionic bonding. Predominantly these are metallically bonded materials. So now we will look at the case of what we call as covalently bonded materials. And this is again an important class of materials, because there are a lot of materials which occur which have covalent bonded. For example, you take you take group 7b. So 7b will mean basically halogens, right? So your Cl2, your Br2, F2, I2 in solid state, they are covalently bonded and they make a particular crystal structure which is based on covalent bonding. Similarly, if you look at group 6b, 6b will have molecules like S8 or even H2O. So H2O will make, for example, a hexagonal ice crystal, right? So these are also covalently bonded materials. These are not something that we use in routine basis. Group 5 elements such as phosphorus, arsenic, bismuth, antimony, they also have strong covalent character, and they basically have these sheet like layered structure in which each atom has 3 neighbors. So it is a layered structure. Each atom having three neighbors. And then the most famous is group 4. Group 4 contains your silicon, carbon, silicon carbide, solid solution of silicon and compound made by silicon and carbon. These are all diamond structured materials. They are covalently bonded, very strongly covalently bonded. And then we have compounds. So compounds, for example, you have 4,4 compound, which is silicon carbide. Then we have 3,5 compounds, things like aluminum phosphide, aluminum arsenide, your gallium arsenide. These are all famous semiconductors. They are 3,5 semiconductors. They are strongly covalent in nature. Then we have 2,6 compounds such as ZNO and ZNS. These are also strongly covalent. Then we have 1,7 compounds. These are CuCl or AgI and so on and so forth. Okay. The covalent bonding typically takes place by, so the theory which is about covalent bonding is called as valence bond theory. Now this valence bond theory basically started with people like Linus Pauling. He was a famous physicist or chemist, you can solid state quantum mechanics person. So he said that a covalent, they said basically Linus Pauling and let us say others. Okay. So a covalent bond would form when the orbitals on the atoms would interact with each other. Okay. So for example, if you take, and this orbital will depend upon how they align with each other. Okay. So if I give you the example, for example, in case of hydrogen, so when orbitals interact. Now this valence bond theory has undergone several modifications. The reason for that is earlier atomic orbital interaction was fine, but there was no concept of orbital hybridization. So it was reasonably straightforward for spherical orbitals to interact or linear orbitals to interact, but when it came to things like silicon, when it came to things like methane, the question was why would something having 2 electron in the outer shell make 4 nearest neighbors, and that would not be possible until you have sp3 kind of hybridization in the system. So hybridization concept came later. So this modified, so I can write here valence bond theory and modifications thereof, which was based on hybridization basically. So it is not only just orbital interaction, it is also orbital hybridization which leads to better orbital interaction, if we can say that. So, for example, if you take example of hydrogen, so hydrogen, we know H atom is 1s and another H atom is again 1s, and if you put these two together they form, so there is this overlap of orbitals and they will have, I mean you can put it this way, but when they interact with each other, one spin would be up, another spin would be down. So, this would be H and they would form what we call as H2 molecule, which is covalently molecule, and you can see that the orbitals can interact with each other because they are spherical orbitals, symmetric orbitals, and they just have to share one electron each. For example, if you take case of hydrogen fluoride, hydrogen fluoride has a H atom here, but the problem with F atom is F atom has p orbitals through which it has to interact, but it does interact with p orbitals. So, it will interact with p orbital, something like that. So, you have at the center F, there will be this another orbital. So, this would be F, okay, and then you have these axes x, y and z axis. You have total of 6 orbitals. So, I am not drawing all the orbitals, but if I put them in different color, so this would be, okay. So, you will have a spin, so if you just put a spin there, there will be one spin up, another spin down, and this would make, so this is F molecule, this would make HF. This is again a covalently bonded molecule. Similar examples you can give for fluorine, for example, F2 gas. So, F2 gas has again F, it will have one orbital on this side, another orbital on this side, and it will interact with the neighboring fluorine atom, which will have p orbitals like this and the orbital like this. Of course, you will have other two axes as well, okay, and this will give you F2 molecule, okay. So, this is fine, but the problem arose with, for example, things like silicon or let us say CH4. Methane is a good example. So, or in carbon compounds, carbon has a configuration of 1s2, 2s2 and 2p2, and we know that CH4 in CH4 carbon will make 4 bonds. In carbon or silicon also, diamond or silicon also, it makes 4 bonds. The question is, why will it make 4 bonds? So, and how will the orbitals align with each other then? And the measured angles, bond angles are 109.5 degrees. These are bond angles in this 4-fold coordinated structure. So, for example, if you look at the top view, this is carbon, you do not have hydrogen sitting like that. They do not make, if you look at the top view, this angle would be 90 degrees, they do not make 90 degrees. So, this is like 90 degree, according to valence bond theory, this should be 90, this should be 90, this should be 90, this should be 90, but then if it was 90, then how come it is making 4 bonds? Because 4 bonds mean carbon will have to share the 4 electrons. Where do those 4 electrons come from? So, these were the questions which led to sort of modified theory, and this led to, so this is what gave rise to questions. The questions were, how could carbon make bonds with 4 neighbors? How could one have bond angle of 109 point, I think it is nearly 5 degree. So, these were the questions, they led to the answers in what we call as now hybridization. So, there are various kind of hybridizations which occur. So, for example, so basically it is S and P type of hybridization. So, you can have sp hybridization, you can have sp2 hybridization, you can have sp3 hybridization. The hybridized s and p orbitals give you the enough number of electrons so that you can have sufficient number of neighbors to make that particular structure. So, that for example, the covalently bonded structure. So, in case of methane, the structure looks something like this. So, you have this carbon atom sitting here, the hydrogen atom is here, one hydrogen atom is here, next hydrogen atom is here, another hydrogen atom is here. So, this is hydrogen, this is hydrogen, this is basically what they make is a tetrahedral kind of structure. So, basically this is a tetrahedral kind of coordination. So, essentially what happens is that you have one s orbital, this is s, okay. So, this is 2s orbital. You can have 2p orbitals as for example, you can have if this is my x axis, I can have one p here, this is along the x, I can have another p along. So, let us say this is y, okay. So, this is y and then another p can be along z. So, you can have these lobes of p orbitals along z. So, this is 2s, this is 2px, 2py and this is 2pz. So, hybridization basically gives you, so if you look at the energetics, so this is for example the energy scale, the isolated carbon atom has, so this is 2s of isolated carbon atom, okay. This has spins like this, okay. This is satisfied, all right. So, whereas in case of p we have 3 orbitals, this is up and this is empty, okay. So, this is x, this is y, this is z and this is 2p, okay. All of them are 2p, 2px, 2py, 2pn. So, when they hybridize, when they go to hybridized, when the hybridization happens, in case of hybridization what happens is that you make a sp3 kind of hybridized orbital like this. So, this is we say as sp3 orbital, okay, and this what you form is basically 4 sp3 orbitals. So, you have 4 electrons here, each of them remains unpaired in these ones. So, this is what is orbital hybridization. So, essentially what you will have is, now you will have one hydrogen will come and attach to it. So, this is another hydrogen will come and attach to it, this hydrogen will come and attach to this. This is how you will make a methane molecule. So, methane will now interact in such a fashion, so that you will have one central atom here, methane carbon, and this will have bond with one here, one here, one here. I mean, I am showing the top view, another would be somewhere here, and they will make an angle such a fashion, so that the angle between each of them will be 109.5 degrees. So, these are all tetrahedral bonds. So, this is basically you can say it is a sp3 hybridization in CH4 molecules. This is what same happens in diamond, which makes or silicon. So, in case of diamond and silicon also, so in case of methane, this would be carbon, this would be hydrogen, this would be hydrogen, this would be hydrogen. In case of silicon, you will have, so if I just make a tetrahedra, okay. So, this is tetrahedra that we can have. This is one silicon, this is another silicon, this is another silicon, this is another silicon, and one silicon will be sitting somewhere in the center. So, this is again a silicon, and again they make a tetrahedral coordination by virtue of sp3 hybridization, which would not be possible just by orbital overlap. Okay.
Can we understand this hybridization in terms of energetics?
There is a energetics, of course it leads to lowering of energy, but I am not covering in this course because it is too extensive. But any basic book on, for example, if you do any basic book on chemistry, the BSc first year level chemistry, that will give you insights into that. So, for example, I think book by Atkins should be sufficient. I can't remember the names right now, but there are a few books which deal with this. Any chemistry undergraduate books will give you introduction, and there are a lot of theories. It's not just one theory. You have valence bond theory, which is modified. Then you have molecular orbital theory. There are a lot of theories in covalent bonding. So, I am not going to get into all of them, but yeah. So, essentially you can say it looks like this. You have one lobe like that, another lobe like that, another lobe like that, and another lobe like that. So, this is the vertical one which will interact with one hydrogen. This is another one which will interact with another hydrogen, and at the center you will have C, and all of these will have angles of 109.5 degrees. So, these are all hybridized sp3 orbitals. They are not exactly p orbital. Okay, these are all hybridized orbitals. So, what you see here, this one, this is a hybridized orbital. Okay. So, you can have other cases as well. You can have, for example, sp hybridization also. You can have sp2 hybridization also. I will leave it to study. For example, graphite will not have sp3 hybridization. Graphite has only sp2 hybridization, and there are some other materials which will have sp3 hybridization. So, I will probably and the bond which forms between these is called as sigma bond. Okay, and sigma bond is a very strong bond. There is another kind of bond which forms in molecules, which is called as covalent bond, especially in polymeric materials. So, you can have if you look at, so you can have these p type of lobes. Okay. So, suppose you have these p type of lobes along the chains of a polymer, okay, like this. The bond which forms between these and the neighboring ones is called as pi bond. Pi bond is a weak bond and sigma bond is a strong bond. So, these are the two terms that you will come across: pi bonds, sigma bonds, and pi bonds. Strong, basically along the axis, and these are weak. You can say these are basically at the periphery. Okay. All right. So, typically you will see if you have sp hybridization, then the configuration will be linear. So, if I write the configuration, sp will lead to linear configuration. So, it would be something like that. This would be the linear configuration. If you have sp2, you will have triangular. So, things like this, and these angles will be 120 degrees. Okay. So, for example, in graphite you have, okay, and if you have tetrahedral, then it is sp3. So, that I showed you. You have one lobe here, another lobe here, another lobe here, another lobe here, and these angles would be 109.5 degrees, close to 109.5 degrees. Okay, and there are some other as well. For example, you can have sp3d and sp3d2, which I am not going to get into. Okay, they are more complicated to draw. So these are some examples of this is basically the basis of covalent bonding, based on the theoretical background. So there are the covalent solids. Now when we come to materials, the covalent solids that we come across, we start with for example graphite. So graphite is a form of carbon. Okay, it has these hexagonal sheets. So you have these hexagonal sheets of graphite. So we can see that each having how many neighbors? So if you look at this, it has 3 neighbors. It makes an angle of, so this is sp2 hybridized structure, and each of these layers. So when you put these layers, so if you now look at the cross section, so these are the layers. So this is one carbon layer, this is another carbon layer. So within the plane they are covalently bonded, and between the plane they are van der Waals bonded. So that is why graphite has this, so graphite makes a unit cell whose C axis is about C length is 0.67 nanometer, but graphite is, so within the plane you have sp2 bonds, between the layers you have van der Waals bond. As a result, graphite has this very nice tendency to make slippery compounds. So that is why graphite is used as a lubricant, because graphite can be sheared easily because of van der Waals bonding. So within the sheet is strong, it makes strong covalent bonds, but sheets themselves are not bonded strongly with respect to each other. So graphite tends to shear very easily, and that is why it is used as a lubricant. Now in the next lecture we will discuss about another form of carbon, which is again a covalently bonded solids, and that is diamond, which is sp3 hybridized material, and perhaps we will also look at some other structures of carbon if possible. Okay, thank you.